Okay, we are back for part 2 of today's lecture. I've gone and picked up my offspring from the bus, and now they're back unsupervised upstairs. So what's the worst that could happen? Let's go into now the final part of colligative properties that I want to discuss today, that being osmotic pressure. And so I realized that we kind of went through the other colligative properties quickly and only did maybe 1 or 2 problems for each. But the plan is to have a lab next week for freezing point depression. So you'll have a chance to work with this equation more carefully. There's also the homework assignment that I posted this week that will give you more problems with these kinds of calculations. And again, if any of those problems that I skipped over in the slide deck are ones you want to work on and then discuss, please come see me during office hours on Wednesday. Okay. Let me find my slide deck and we'll get started. So the last colligative property that I want to discuss is osmotic pressure. Okay. You've all probably heard of osmosis and how it is, in the context of learning through osmosis, right? Just sitting there and letting the knowledge diffuse into your brain, and then you have it there without any work put into it, right? Osmosis is essentially the transfer of molecules through a semi-permeable membrane, okay? And it's driven by the process of diffusion. And I know that you guys have talked about diffusion and effusion in Chem 101. So hopefully that process is at the forefront of your minds from having learned it not long ago. When we talk about osmotic pressure specifically is the pressure that is applied to some solvent in its pure form that prevents it from passing into a given solution by osmosis. Okay. So in other words, it's the pressure required to prevent osmosis. Okay. So we talk about it as in terms of concentration of a solution, right? So we can set osmotic pressure equal to the molarity of the solute times the universal gas constant times temperature. So molarity, M, temperature, T, are universal gas constant. Okay. Now, the image on the left is of a pure solvent on the left side of the semi-permeable membrane, and then a solution on the right side, okay? And then that is without any osmotic pressure, and as you can see, the two levels in this U-shaped tube are the same, okay? Right here. They're at the same height, right? But the one to the right, now when we have osmotic pressure that's happening, it's driving an imbalance on each side, right? And so now we have a higher level on the solution side. And what's driving that, right? Pressure. Okay, so now there's an imbalance in the relationship of the pure solvent relative to the solution. And now that solvent isn't going to pass through or diffuse into that semi-permeable membrane. So it's not evenly balanced between the two. Oh, I see. That's because it's got my annotation on. Sorry. Let's clear that up and go. Okay, so how do we apply this concept of osmotic pressure? Well, osmotic pressure is going to be in ATMs or torr or kilopascals. And this question, it's saying that we have 0.3 molar solution of glucose, and that's going to be in water, and we're going to use that as an IV in a patient that has a body temperature of 37 degrees Celsius. What is the osmotic pressure in atmospheres? Okay, so to solve this, you have molarity, you have temperature. What you need to do is figure out the gas constant and put those together, and that should give you osmotic pressure. So I'm going to pause it here, write a little bit on the board, and I want you guys to work on this, and then we'll work on it together. Okay. Okay, so this is our equation. Osmotic pressure equals molarity times gas law constant times temperature. And so what are we given? We're given that the molarity is 0.30. And that the temperature is 37. Now, as with most of these things we've been working with, in order to apply it with the gas law constant, right, it has to be in Kelvin. So plus 273. And then the gas law constant is what? 0.0826, right? Liters, atmosphere per mole. Okay. And we just put those things together. So it's going to be 0.30 moles times 310 K times 0.0826 liters. Okay. And again, we're looking for atmospheres, right? So hopefully all of this stuff should cancel out. We missed just atmospheres. Let me crunch this. So 0.3 times 310 times 0.0826 gives me 7.6 atmospheres. Okay. And this should all cancel out, because what is molarity? It's another way of writing that. Oh, you can't answer because it's recording. I'm just by myself. But molarity is, remember, moles of solute over liter of the solution, moles per liter. So we could write this as moles per liter. And now what cancels? Moles here cancel, liters here cancel, and K cancels. And we're just left with atmospheres. Okay. So very simple, just straightforward plug and chug kind of problem here. All right. Where is the slide deck? Okay. How about this one? The osmotic pressure of a solution containing 5.87 milligrams. We're going to have to do something with that. Of an unknown protein per 10.0 mils of solution is 5.45 torr at 25 C. Find the molar mass of the unknown protein. That's going to be tricky. Okay, so it's giving us the osmotic pressure of 2.45 torr. And it's giving us milligrams per mil, which hopefully you guys know what to do with there, right? We can convert these to get at molarity. And we have temperature, right? And so let's see what you come up with. Pause it, give it a go, and then we'll go over it together. Okay, so this is the information that we're given. Well, we're given 5.87 milligrams of an unknown protein, 10.0 mils in the solution, 2.45 torr as the osmotic pressure, and the temperature is 25 C. Remember our equation, osmotic pressure equals mRT. What we need to do is find molarity. We have temperature, 25 degrees. We have our gas law constant, and we have osmotic pressure. So we rearrange that equation to be what? M, molarity, equals osmotic pressure over RT, right? Okay. And so what is our osmotic pressure? 2.45 torr. Okay. What is our gas law constant? 0.0826 liters atmospheres per mole K, right? Now, hopefully you can read that. Yeah, get a little bit more clear for you. 8.0826 liters times atmosphere over moles times K. And then we also have temperature in Kelvin, right? Which is 298 because it's room temperature. Okay. Now, one thing doesn't jive here. That's that we're giving torr, okay? But our gas law constant is in atmospheres. So we just have to use our conversion factor, right? We know that 760 torr is equal to 1 atmosphere, okay? So up here, we can just do 1 atmosphere over 760 torr. That'll cancel out the torr and give our units of atmosphere up here so that everything is copacetic, okay? Let's crunch that and see what we get. So 2.45 divided by 60 divided by 0.0826 divided by 298. I'm getting molarity of 1.31 times 10 to the negative 4. Okay. So that is our molarity. They're not asking for our molarity though, right? What are they asking for? They're asking for the molar mass of this unknown protein. Okay. So this is part of it. We got to now take this and apply it to the next step. Okay. So we know that molar mass is essentially going to be the mass of the protein over the moles of the protein. Okay. What's the mass of the protein? 5.87 milligrams, but we can't leave it at that because it's in milligrams. We need it to be grams, right? So let's make it molar mass. Just screw it down. Molar mass equals 5.87 times 10 to the negative 3 grams, right? Because it's in milligrams. So it'd be 10 to the negative 3 grams over our molarity. Because what is molarity again? It's moles per liter, right? This is moles over liter. Okay. And what we're saying is that we have essentially 1.31 times 10 to the negative 4 moles per liter. Now, what did they give us? They gave us 10.0 mils of solution. So we got to see how many moles this is in respect to that number of milliliters. Okay. So before we put anything down here, we've got to do a conversion factor, right? We got to convert 10.0 mils to liters and then multiply it by this conversion factor, right? So we could just say 10.0 times 10 to the negative 3 is milliliters to liters. Or if you wanted to write it out, we could do the conversion factor of, hold on a minute, my units. 10 mils times 1 liter over 1,000 milliliters, and that will essentially give us 10.0 times 10 to the negative 3, and then that converts this to now liters, and then we multiply that by our molarity, which is 1.31 times 10 to the negative 4 moles per 1 liter. Because remember, molarity is moles per liter. Okay. What cancels out? Our mils cancel, our liters cancel, and it just gives us our moles. So 10 divided by 1,000 times 1.31 you can probably do this in your head because it's nice, friendly numbers here. That's 31. Yes, as I thought. 1.31 times 10 to the negative 6. Okay. So 1.31 times 10 to the negative 6 moles. Okay, and so if we do that, if we do 5.87 times 10 to the negative 3 divided by 1.31 times 10 to the negative 6. We get 4.48. 4.48 times 10 to the third grams per mole. And that is the molar mass of our unknown protein. So pretty cool how this is all interconnected, right? We can determine what a substance is by looking at how it behaves given a certain amount of it, how much of it is in solution, the temperature, and the pressure. And all of that can give us the molar mass. And then, of course, if you were to look up the molar mass, you could probably figure out what unknown protein that is. Okay. Not drinking beer. I'm drinking spicy water, just so you know. Okay. Oh, and spicy water. I guess that's what my kids call it. They call it spicy water. It's actually sparkling water, I guess. Just to clarify. Hold on. Where's the slide deck? I think that's about it, really, guys. I've covered most of what I wanted to. And so briefly wanted to touch on reverse osmosis, because that's just a way to apply pressure greater than the osmotic pressure of a particular solution to drive that solvent back through that semi-permeable membrane. Because remember, osmotic pressure is the pressure at which you don't get that diffusion. So there are these reverse osmosis machines that are used oftentimes in labs to purify water by taking it and applying pressure to the system such that it's greater than the osmotic pressure of water. And so anything that's dissolved in that water is going to be pushed through that semi-permeable membrane. And then, the solvent will be pushed through the semi-permeable membrane, and then you have purified water. Okay, so it's just another way to get the things out of water that you don't want to be in there, whether it's microbes or deionized water, the filtered water, distilled water. All of these are different techniques to get water alone, right? And so reverse osmosis is a process to do that that's commonly used in labs. Not that you really need to know that for a test or anything, but just for your own information. If you end up joining a lab or go on and do research elsewhere in a four-year college or whatnot, and there's a RO water, that's reverse osmosis water. Okay. So that wraps up this colligative properties lecture. Again, any questions on these problems, feel free to come seek me out. We'll be doing homework with this and some ICAs with this, and hopefully another virtual on-campus lab with this. And therefore, there should be plenty of practice with these types of problems. Okay, so have a wonderful, safe weekend, and I'll see you next week.